So take 4. Hopefully we don't get interrupted trying to do this. I've been interrupted 3 times trying to start this video. New unit is called quadratics. They're a type of function. Everything we've done to this point has been a linear function. It made a straight line. Now we're going to talk about quadratic functions. They are curves. So we're away from the straight line part of algebra and into the curvy part of algebra. Before we get too far into this, you should know that all of these notes have been converted into a PDF document. It's up on Edline. You can go grab it so that you can take the notes on it. You don't have to, but there are several graphs that we're going to be doing, and so you might want it just so that your graphs can look pretty, but like I said, it's not necessary. It is there, though, if you want it. So, quadratics. We're going to start out by talking about what the parent function is. Y'all have heard this before. We talked about the linear parent function way back when we were talking about linear functions. And if you'll remember, the linear parent function was y equals x. And it was a straight line that went through the origin and had a slope of 1. The quadratic parent function, since we're now talking about curves, is y equals x squared. So this is the quadratic parent function. And you can see I left the table all filled in because I keep getting interrupted. And so if you look, you can fill in the table. And here's how I got these values. If x is -3 and my function is y equals x squared, well, -3 squared is -3 times -3 gives me +9. And then -2 squared is 4, and so on. And so I filled in the table, and I'm going to use these values that are in this table to make a graph over here so that you can see what the quadratic parent function looks like. So I'm going to plot the 0, 0 point first. And then I'll start with these. So I have -3 and 9. I have -2 and 4. And then -1 and 1. And then on the other side, so you can see these numbers are nice. They're symmetrical. On this side of 0, you have 1, 4, 9. And on the other side of 0, you have 1, 4, 9. So it's nice and symmetrical. And the reason why that is because quadratics always make pretty symmetrical graphs, which means I could cut them in half and the left half looks exactly like the right half. They have nice, pretty symmetry. So I'm going to connect these dots so that you can see the curve. And when you connect your points to make the graph, make sure you connect them in a smooth curve. You don't want it to be a sharp line. It should not be a V. That's a completely different kind of function. It's a curve, so it doesn't have to be all ugly like mine, but you know, try and make it pretty. You should connect them in a smooth curve. Now this curve, y'all have seen curves like this before. When we did talk about domain and range for the first time, we saw curves like this, and I told you then that the name of this curve was a parabola. Not parabola, parabola. So you have seen it before, it's just been a while. So let's review domain and range first, since we are talking about this. We have this pretty parabola right here. It's the graph of the quadratic parent function. And if you remember, the domain of any function is all of the x values that function passes through. Well, because this parabola has arrows on both ends, that means that it's going to extend to the left forever and to the right forever. So my domain goes from -infinity to +infinity. So it is all of the real numbers you could possibly think of. So the domain is really all real numbers. That's one way to say it. But it goes from -infinity to +infinity. Now the range, if you'll remember, is all the y values that a function covers. And so this function right here of this parabola starts at 0 and extends upward in the upwards direction forever. So the range goes from 0 all the way to +infinity. And so that's the range. Another way to write this, because you're going to see it written more than one way, you could also say that y is all of the numbers that are greater than or equal to 0, because it starts at 0 and goes up forever and ever. So you could just write it as simple as this. Both of these are correct. I wouldn't count this wrong, but just know this could show up. Now every parabola out there has what we call a vertex. It is the lowermost or uppermost point of the parabola. The vertex for this one happens to be this point right here, and so my vertex is at 0, 0. We call this vertex a minimum because it is the lowest point on the graph. Now concavity, that's a new word for you, at least in math. You may have heard about concave things in science. It has to do with how the roundness of something. In this case, this parabola opens upward because when it opens it goes up, and so we say that its concavity is that it opens up. And so its concavity is, it is concave up, is how we would say that, because it is opening in an upward direction. Now, we talked about the symmetry over here a minute ago with the table, and also as I was graphing it, I talked to you about the symmetry. Every parabola that exists has a line of symmetry that cuts it exactly in half. And if you will look at the parabola that we have drawn, the line of symmetry is right here. If you could draw a straight line, not like me. It cuts it directly in half so that the left side of the parabola matches the right side of the parabola, as long as you draw prettier lines than I do. The line of symmetry for this parabola happens to be the y-axis. But I can't just write y-axis. I've got to give it an equation. And so the line of symmetry, every line of symmetry that you have to do, is they're always going to be x equals, because parabolas can't have a line of symmetry that is not a vertical line. It will always be a vertical line. And in this case, it's x equals 0, because it passes right through where x equals 0. So the line of symmetry is x equals 0. That's the line that cuts it in half. So when I say line of symmetry or axis of symmetry, that's what I'm talking about, is the line that cuts it in half. Let's do a few more definitions just to make sure that we have them. We've talked about this point right here. It's the vertex. It is always either a maximum or a minimum. We'll refer to it either way. This one happens to be a minimum because it's on the bottom, but if the parabola went the other way, then we would call it a maximum. Right here where it is pointing to this -1, this is going to be the line of symmetry. As if I drew a line right here, it would cut that parabola directly in half, so the left looked just like the right. Now these points right here, this one and this one, they have several names, but they all mean the same thing. I'm only going to fill in one of the boxes because the same thing goes in both boxes. This, where it crosses the x-axis, these are both going to be identical, but the point where this graph crosses the x-axis, sometimes we call it a solution. So it's the answer to a quadratic, and you'll see that it has two of them. It's because it's an x squared function. Sometimes it is also referred to as a root. So if I ask you to find the roots of a function, that's what I'm asking for, is the solution. Sometimes they are also called zeros. And the reason they're called zeros is because they are the point where y equals 0. And so all three of those words refer to both of them. And so the same three words go in this box over here, solution, root, and 0. But these two things, they have several names that all mean the same thing. So line of symmetry. We talked about it a little bit on the first little graph that we did. The line of symmetry is just the line that cuts the parabola in half. And so you can write that down if you want, but it's the line that cuts the parabola in half. And there is actually an equation you can use to find the axis of symmetry. If you have a quadratic that is in this format, ax squared plus bx plus c, where a, b, and c are all integers. They're just numbers of some sort. And y'all are used to this ABC thing because you've been factoring for a while and you know that you know all about a and c. The equation for the axis of symmetry is always going to be x equals, because it is a vertical line that cuts the parabola in half. And the equation for that is the opposite of b, so whatever b is, divided by 2a. You need to commit this equation to heart. You're going to have to use it over and over and over, but to find the axis of symmetry, it's the opposite of b over 2a. So we're going to use this equation over and over. We're going to practice finding the axis of symmetry for some graphs, because you don't always have a pretty little graph like this one. This one does have a graph, and if you wanted to write the axis of symmetry, or the equation for the line of symmetry, this is the line that cuts it in half, and if you'll look, it's at x equals -1, -2. And so that's your equation for that axis of symmetry, but you don't always have a graph. Sometimes all you're given is a function, and you are asked to find the axis of symmetry. Now the first one that's thrown up there is kind of icky, but it's not so bad. Okay, but it does have fractions. It is not the end of the world. We're going to start by writing down our formula, which x equals the opposite of b over 2a. And if you will look at the function that you have, here is a, here is b, here is c. Well, so b is 1/3 because it's the number in front of the x. So the opposite of b is -1/3 divided by 2 times a. Well, in this case, a is -2. So I'm going to have to do 2 times -2. Never fear, I know there are fractions, it's okay. So I end up with -1/3 over, when I multiply 2 times -2, I get -4. So I have this division problem. I have -1/3 divided by 4. two ways to approach this. You can grab your calculator, type in -1/3 divided by 4. You can remember what you learned last year or even before that about dividing stuff with fractions. And so this really means -1/3 divided by -4/1. And if you will remember how we divide with fractions, we keep the first one, change this to multiplication, and flip over the second one. And so now I can multiply. Well, this becomes -1 over -12, which is 1/12. So the axis of symmetry for this line is x equals 1/12. It's not even right on a point. This is part of the reason why we didn't just use the graph, because on the graph, I don't know where to find 1/12. That's kind of a hard one to find on the graph. But from the function, I can get that the axis of symmetry is at x equals 1/12. And so it's somewhere between 0 and 1, closer to 0 than it is to 1 on the graph, but it's a vertical line right there. Now, this next one, y equals x squared minus 7. It only has two terms. It does not have three, so finding a, b, and c is a little difficult. So I'm going to rewrite this as x squared plus 0x minus 7. Because that middle term is not there, so we're going to treat it like it's a 0. So to find the axis of symmetry, I have x equals the opposite of b over 2a. Well, the opposite of b in this case is just 0, because 0 doesn't have an opposite. Okay? So the opposite of b is 0, and then 2a, well, there's no number in front of the x squared. That's because there's an invisible 1 here. So it's 2 times 1. So I end up with 0 over 2. And if y'all can remember division rules, 0 divided by 2 is 0. So the axis of symmetry for this is x equals 0. And if you'll remember from our first example, that just means that it's the y-axis, because x equals 0 is the y-axis. So that axis of symmetry for that one is at the y-axis. There is one more example down here. I'm going to leave it there and let y'all try it. See if you can find the axis of symmetry. So pause really quick, see if you can find the axis of symmetry, and then come right back. So the opposite of b for this one is 20. And then 2 times a is 10, because 2 times 5 is 10. And when I simplify that down, I get 2. So the axis of symmetry for this is at x equals 2. Hopefully that's what you came up with. Let's talk about just a few more things. Axis of symmetry is the big thing, but let's toss it all together, okay? We have this pretty little graph. It's all graphed all for us. This is the function, x squared minus 4x plus 2. And the first thing it asks for is the vertex. Well, the vertex is this point right here, which happens to be at 2, -2. And so there's my vertex at 2, -2. Now, then it asks for the line of symmetry. Well, I'm going to show you something really nifty about the line of symmetry. But first, we got to talk about this vertex. Is it a minimum or a maximum? Well, it's a minimum because it is the lowest point on the graph. Now, the line of symmetry, I have the function. You can do the x equals the opposite of b over 2a. So x equals the opposite of b is 4. 2a ends up being 2 times 1. So I have 4 over 2, which is just 2. So the line of symmetry is at x equals 2. Look at your vertex. What is the x-coordinate of your vertex? The x-coordinate of your vertex is 2. So if you know your vertex, the line of symmetry is just the same thing as the x-coordinate of that vertex, and that's because the line of symmetry passes directly through the vertex. And so they're the same thing. It's one way to do it. Now the concavity, this opens up, so we say that it is concave up. And then it asks for the domain and the range. Well, the domain goes from -infinity to +infinity, and my range starts down here at -3 and goes up for, -2 and goes up forever. So it's from -2 to infinity, or I can say y is everything bigger than -2.